So first of all, a bit of an industry context from the recent NACE impact study, and Jeff alluded to it earlier. If we were to extrapolate in the New Zealand industry, the cost of corrosion sits between media and telecoms and mineral and oil extraction industry. So it's a reasonable size. It's up until recently was around about our fourth largest export. And of course, we're here today because we have many firms that we're operating in that particular space. So it's not insignificant, and it's a very good industry. Just starting at the beginning, I thought I'd put the definitions of corrosion and passive fireproofing together, because often we come across coating specialists and then passive fireproofing specialists. But when we do install a passive fireproofing system, we really have to think about what's sitting underneath. So corrosion defined as the damage or deterioration of material due to reaction or interaction with the environment. And what passive fireproofing does is changes that environment. So the system that we put on as a passive system rather than an active system buys time essentially to a particular standard for an active system then to come in and stop a fire. The corrosion cell, the only thing I want to point out here, many of you would have seen this, is that the corrosion solution, we've got to think about how the passive fire layer changes that I can see Jeff's point. I'm going to have to stand over here. Everybody can hear me? So what we're going to look at today is how we consider the corrosive solution as a in the passive fire system. Just firstly, passive fire systems take into account various curves. These are fire curves. The ones that we mostly consider is the cellulosic fuel source and the time it takes to generate maximum heat, and then the hydrocarbon, and then the modified hydrocarbon, which is a concentrated form of fuel, possibly jet fire, for example. So when designing or specifying a passive fire system, we've got to take into account the source of the fuel and how it behaves. So you can see that at its maximum, the cellulosic fire reaches just over 1,000 degrees Celsius over a period of time. Hydrocarbon around about 1,100, and then the modified hydrocarbon around 1,300 degrees Celsius. But what about steel? So the structural steel begins to lose strength from about 300, begins to degrade from 400 degrees Celsius, and by around 590 degrees Celsius, failure under load. So if we think about a tank on stands, it's the last thing we want when we look at the temperature that the petrochemical fire is reaching. So it really just buys time for the active fire systems, such as your respondents, foam systems, carbon dioxide, and sprinkler systems to act. We certainly don't want that to happen to our assets, so we really have to consider what's happening underneath the passive fire layer. So, according to the American Petroleum Institute, recommended practice 583, they consider corrosion under fireproofing similar to corrosion under insulation. So the mechanisms, and if you think about it, passive fireproofing is really a thermal barrier. And so the same mechanisms are happening with regards to corrosion under insulation and corrosion under fireproofing. Different products, of course, but we need to think about the mechanisms of corrosion. Firstly, I'll just take you through a couple of systems. So intumescent paints, they rely on an ammonium compound to form a charge during elevated heating from a fire. And you get different types of paints, some that activate at about 65 degrees Celsius and most around about 150 or so. So depending on which situation you need. And they can expand up to about, depending on how much you put down and the formulation, anything from about 5 to 50 times its original thickness. And activates firstly by acid release and then a gas production, and then it forms this char layer. Plaster-based passive fire systems, or non-intumescence, for example, the most popular being of the coating systems are the Portland cement-based formulations, and there's a whole variety of formulations which change the density, hardness, flexural strength, and thicknesses. The density, for example, normal cement for a 50 mil layer could be around about 125 to 150 kilograms per metre squared. These can be reduced down with the additions of products like vermiculite and perlites, additives, etc., and various other permitted flavourants and colourings, to around about 25 to 50 kilograms per metre squared. So if you're thinking about a structure that's being coated in cement, you think about the supports and the loads that are required. It's quite significant when you talk about cementitious coatings. But of course, a cementitious coating is not so susceptible to chloride and chloride ingress, or sort of swapping out these ammonia compounds in intumescent, for example. You also get gypsum-based plaster, fibrous-based plasters, often come in the form of boards. You'll see that around certain columns, etc., particularly in commercial projects. I can't go and not talk about blanket systems, because they're reasonably popular around complex structures, particularly in oil and gas. And the beauty of these systems is that you can take them off, inspect, and put them back on again. They operate in the same way, that they form a thermal barrier to a fire. They utilise a variety of mixtures of fibres and essentially form a sort of an air barrier. Of course, the key ingredients for a cementitious-based passive fire system is pretty simple, really. You've got a lath, or a lath, depending how you want to say it, which is it's a more substantial grid system with which to build your cementitious layer on. There's actually a good example just in the room next door there, as well as a mesh as well. Your product and decent sized or decent equipment with which to apply. And of course, one of your most important ingredients is your skilled team and trained team. So with that, you can then sort of form your profiles around your structure, and then build up your passive fire layer. Here's a couple of pictures of forming. You'll notice some boarding underneath there. That's to provide obviously to support an application under a vertical, an upside down application, but also to provide a bit of a finish. There's an operator starting the process. Trowel-offs also leave a nice architectural finish, depending on what the customer requires, whether they want to paint things on there, etc., or put signs. Here's a typical tank with its support that's been passive fireproofed. But this has an effect on the underlying, passive fire systems can have an effect on the underlying steel, particularly if you've got obviously fire damage. You don't quite know what you've got underneath. If it was a minor incident, for example. Deluge erosion in bunding areas, etc. Something just to be aware of. Weathering, UV, temperature, moisture, and immersion. The weathering of the cementitious systems is a lot better than intumescence, which generally tend to be used indoors or undercover. Movements, and you'll probably appreciate that the mesh system does add a bit to the movement resistance or of the actual cementitious system, and of course a down and dirty application, which is what we want to try and avoid when we're looking at a contractor. And the role of the top coat, which I'll talk about a little later, we often put top coats because to seal the system for colour protocols, signage, etc. But does that have an effect on the corrosion mechanism? We'll go through that shortly. So the challenge, of course, is applying these systems in a complex environment. Here's a cracking unit with a passive fire system protecting its base, and then it's got an insulation system all the way to the top. So, the applicator and how they operate, the meshing of the structure, the actual initial application of the system around tight corners in small spaces, etc. And of course, this is the weathering. Most systems, this is actually an intermittent system, but most systems are pretty well, they still perform okay after a period of time despite weathering, but not corrosion. And I think all I wanted to emphasise here is that what happens underneath actually has an effect on the performance. So this and the next one as well, these were tests done in a laboratory a couple of years ago where they established that managing the corrosion under the passive fireproofing is critical for the performance of the fireproofing itself. And that's really the point I'm trying to get across. What we want to prevent is moving the corrosion beyond point B. So in a corrosion under reinforcing bars, for example, this is the closest model I could find for that propagation of corrosion in a cementitious environment. Really just, we need to be able to make sure that we're not causing any corrosion of both the subsurface and the system holding the cementitious fireproofing together. Here's a couple of examples of a system that's clearly corroding, and then one that's been removed showing the underlying damage. We don't want our vessel or asset to look like that once we've been able to remove the system. So how do we prevent it? Well, first of all, let's understand what it is. So as you can appreciate, we want to prevent an annulus space for water or contaminants to reside. We don't want any contaminants from the passive fire system to damage the coating or influence the coating in a negative way. And also we don't want the system to wick or absorb water. And on complex vessels, often the finish at penetrations or ports, etc., that's one of the danger areas. So the finishing of it is quite important around those areas to prevent the third movement, the wicking or absorption of water, because it'll find its way through and cause all manner of damage. So the considerations to prevent corrosion and passive fireproofing, despite the fact that the asset may be above ground and may be in a nice, well-ventilated area, we would, well, in this particular case, the asset owner considered an immersion grade coating. Also consider a properly designed weather barrier. And of course your choice of material. It's got to be hard enough to, or weather resistant. And also take the movement, if there's movement of thermal expansion or general movement of plant, etc. So this particular tank, we just did recently, proper forming of for access, and a white blast, 2.5, 8 SA 2.5 white blast. There's a layer put on, I'll get to that shortly. Just to show you quickly the size of the project and the forming of the first layer of passive fire system, getting around the corners, and then the slow build up to the required thickness for the fire resistance time, and then final top coat. And there's actually a different vessel, but I couldn't find one of the other one, of the original one. So on the face of it, the system for the coating underneath the passive fire proofing, we could choose one of two, which would be D and E from the asset owner's specification, because that directly refers to the fire system. However, when it got down to where the vessel was, what the dangers were, they opted for coating system H, which is for buried tanks. Although this is an above ground tank, it was a buried tank specification that we went for. So running counter to what the original specification called for, or running, gone for a bulletproof option, because of the dangers that were identified from the actual system of the passive fire system. So it was a two layers of high build epoxy, around about 650 microns all up, and giving a nice sort of a barrier. So the argument for the top coat, obviously, to identify if there's been fire damage, also to perform as a barrier against any contaminant ingress, also to identify plant codes and colours, etc. Prevent water ingress due to cooling heating cycles and firewater and deluge. Deluge erosion, it's easily identified if you've got a top coat, not so much if you've just got a cement finish. Weathering movement, and also once you put a top coat over, it highlights any down and dirty application. But once water's in, can it get out? Water's going to get in. There's a corrosion and insulation model that suggests that if there's a jacketing, you run the risk of creating this water conveyor belt within the system. So if we think about, instead of a fibre thermal insulation, we're talking about a passive fire system. And you put a top coat over, depending on the breathability of the top coat, and this is where experts like Jeff come in, we could end up with the water being trapped in, and then during heating and cooling cycles actually causing more damage. But we can keep an eye on these sort of things through the use of corrosion probes, for example, if you want to put something permanent, or pulse current system to identify if you've got any corrosion happening. Fortunately, there are a couple of recommended practices and technical groups, and yeah, these are some of them that are starting to get together. The recent NACE recommended practices just been published, the 2017 one, which looks at the system of protecting the underlying steel underneath passive fireproofing. So it's not a hit or miss thing. There is something to consider, or some guidelines, if you will, when considering the corrosion under passive fireproofing. And I think that's it. Thank you. Any questions?
Any questions for?
Yes, sir.
I noticed with the client's specifications, was I reading galvanised steel?
For piping.
For piping. You wouldn't put zinc under insulation.
No.
So that's probably why you went to F.
Yeah. If you read some of the passive fireproofing technology, they just talk about a zinc coating underneath the passive fireproofing, which this asset owner considered was way insufficient for the long term.
Yes, unfortunately, a lot of these specifications hang around long after they've been proven to be correct. The NACE paper you quoted there on corrosion under insulation specifically says don't use zinc any longer. We used to think zinc was marvellous, but it lasted about 6 months.
Yeah.
Rapidly completed in a wet environment.
Yeah, having spent a fair bit of time doing fireproofing systems in the oil and gas sector, the corrosion under insulation scenario with the vermiculite type cement-based systems, what about like the epoxy intumescence for the jet pool and hydrocarbon? Aren't they in themselves a protective coating, as much as that you put a primer down 8 mil of, Jeff's products, Chartex 7 or 1709, really, haven't you got a effective barrier system there anyway, a corrosion barrier system, where you actually get away from the CUI scenario of the fender light type systems where you actually put a coating over the top of it and you can trap moisture in between it?
I think possibly in this situation that that I was talking about, where it wasn't a Chartec, it wasn't just if I remember correctly, customer specified a Solitec system. So they wanted to put down a corrosion barrier underneath for long-term corrosion protection. Whether that was what they considered. I mean,
yeah, I did a lot of work for Shell in Corio plant in Victoria in the late 90s, early 2000s, where we stripped a lot of the old fender light type systems off, and in fact they had that plant down there had concrete encased columns which provided the fire protection system as well. But they used to wash the plant down with salt water in those days, so you had this never-ending battle for corrosion. So what we did is we actually stripped off all the concrete systems and all the fender light systems and reapplied 8 mil of inch and epoxy, and that was the total barrier system in the end.
Yeah. Look, I don't know.
I mean, it's more expensive.
Yeah.
But we actually put in test viewing areas on major support columns so that we can go back and check corrosion rates a number of years down the track. It's interesting that they still use fender light systems because they're easy to apply. A lot of tanks, you know, it gives some thermal quality as well. But there are other systems in there that give you actual barrier systems in the coating as well.
Yeah.
Particularly in that jet pool scenario.
Yep. Yes.
Two questions, actually. In terms of thermal insulation, would the standard code of practice define any kind of thickness? What kind of thickness you got to have, or what's the criteria for it?
I think we're only talking about the corrosion aspect of the similarities between CUF and CUI, but not the thermal performance of the passive fire system. That's a separate issue.
Next question as well, related to thickness, but in terms of inspection, how hard is that to have the inspection windows to have to be inspected, or any
When you say inspection,
of the vessel itself?
right? Well, as Ross said, you might want to put, because it's a cement-based system, it's pretty difficult to get off. So you'd want inspection ports if that was deemed necessary.
That's generally what they were doing, putting inspection ports in.
Yeah. You don't want to take it off. But how do you know what's happening underneath it? And I think considering it at the specification and application stage rather than trying to solve the problem afterwards is way easier, as we well know. Yeah.
Thanks, Ray.
Thank you very much.
Let's put our hands together for one.